Please. Thank you. Sorry, I forgot to write the title on the blackboard before. So thank you for the invitation. I'm very sorry for a very long abstract. I hate it when talks have very long abstracts. And only when I saw the announcement in the email, I was like, oh, wow, I really wrote a very long abstract. So now I will spend half of the talk basically repeating the abstract, but well. Sorry? I read only half of it. Okay, good. So I will talk about Favard length of random transfer sets. And well, a long time will be spent talking in general about Favard length, and then maybe towards the end we will get random Cantor sets. So we'll see. But if we get that far, then this will be based on the work. Ongoing joint work with Chang and Giacomo. Okay. Feel free to interrupt and ask questions at any time. First, what is Favard length? So in this talk, we'll denote by phi theta of x will be following mapping. It's that's the orthogonal projection. The x scalar product of sine theta sine theta. For the period plane, we look at the line and theta, phi theta is the orthogonal projection to this line. Okay, so now having the notation for orthogonal projections, we can define Favard length. So you have a compact set K in the plane. Its Favard length, the integral over all the directions, you define of the length of the orthogonal projection K. So in this talk, we will use also the notation like this for at least for subset of the line. Our length is this integral, so in other words, it's the average length of orthogonal projection. Okay. So maybe a few observations.
Excuse me, so by length, you mean just one-dimensional effect?
One-dimensional effect measure. Yeah. Okay, so some observations about this object. First, the Favard length with some set K. It is the same as looking at the two-dimensional Lebesgue measure at the affine Russelinian. So we look at all the affine lines in the plane. Okay, this is a two-dimensional manifold. We look at the two-dimensional measure on this. And the Favard length of some subset of the plane is the same as the measure of lines which hit our set K. Okay. So this can be seen that you fix a direction, you look at all the lines which hit your set in this direction. That's the how many lines are there? Well, it's the orthogonal projection in the set in direction, and then you look at all the directions. So this is how this can be seen. We won't really need this, but this is pretty neat. And because of this, this quantity is sometimes also called Buffon's needle probability.
You mean that the intersection is not n?
Yeah, sorry, the intersection of yeah. So because of this fact, this Favard length is the second name sometimes used as Buffon's needle probability. Of our fixed set K, because the history is that you have some set maybe in the plane, or well, let's say in a unit ball, and then you drop a random needle on your ball, and then what's the probability that your needle hits your set? So this is essentially the Favard. Okay, so that's one small observation. Second small observation is that if you have a set of zero length, so if I want to look at length of sets in the plane, then maybe instead of this, I will like H1 for one-dimensional Hausdorff measure. So if the Hausdorff measure of a set K is 0, then this implies that the bar length of K is 0. This is super simple, just because the projections do not increase length. The third simple observation, well, this is maybe not so simple, but well known, is that if the Hausdorff dimension of the set K is greater than 1, strictly greater than 1, then this implies that the bar length of K is positive. This is due to Marstrand's relativity. This is one of the parts of the Marstrand's projection theorem. Yes, yes, yes. But there are these. Maybe if you look at set in a unit ball, and you look at the needle of length 2, and then you condition on some. Anyway, yeah. So basically, if I take a zero length, its Favard length is 0. If its dimension is greater than 1, it's a positive Favard length. Really, the most interesting sets for which we want to study this thing, they will have positive length and they will have dimension because then things get more complicated. And in particular, we have the theorem of the convergence. From 1939, which is the following. We have a set that's called K. We have a set K, positive and finite length. Then the Favard length of K is equal to 0 if and only if K is purely undefined. Which means that the intersection of K with any rectifiable curve gamma is equal to 0. There's a 0 length. Every rectifiable curve gamma. Okay. So somehow for this set of positive and finite length, the Favard length is particularly interesting because then it has connection to the geometry of the set. Can detect whether your set is purely undefined, whether the set sees curves. But if you've never seen purely rectifiability, don't worry about that because I will try to keep it dynamical and friendly. So in particular, as a corollary of this result, so in particular, Favard length of K is equal to 0 for all, say, nice self-similar sets dimension. If any set self-similar set of dimension 1, which is nice, that will give us some separation, any such set will be, well, and which is not contained in the line, any such set will be purely unrectifiable. So then, by the convergence theorem, we get that it's 0 Favard. Okay. So far, so good. Can I also write here? Yeah. So one particular self-similar set will be especially interesting to us, namely the four-corners Cantor set. So we are interested in Cantor set. I imagine everyone is well acquainted with, but just in case, how is it constructed? Definition. So you start with a square side length 1, and then its corners, you put the 4 squared side length 1/4, and then you start iterating this. This is called the four-corner Cantor set, and we will denote by Kn the n step of the construction, and that will denote like K the limit. So, thanks to the result of Petrikovich, although there are also simpler results, simpler proofs of this fact that were found later on, we know that the Favard length K. So, almost every line in the plane does not fit this. And almost every projection of K has 0. So, in particular, if you look at the Favard length of this end step of the construction, so you have 4 to the power n squares of side length 4 to minus n. When you look at this guy, then at n goes to infinity, this converges to the Favard length of the limit set, which is we know that the Favard length of these approximations, they converge to 0. Now, here's the question we're interested in. Here's the one. This was posed by Peres and Solomyak in 2002. They asked, what is the rate K rate at which the Favard length can converge to 0? That's the question we have. And this is sometimes called the Favard length problem. By other authors, the Buffon's needle probability problem. Something like this. Any questions so far? Okay, so as a sort of warm up at looking at this problem, let's make a few small observations again. So, some observations. So, yep. I will say something about what I think was their motivation, and which is also my motivation for being interested in it. But I don't know if most people who ended up working on this, if they cared about that. But at least in their original paper, there is this one paragraph in the introduction where they mention something. So I would imagine that was their motivation. But Okay, but yeah, I'll get to that, in a little bit. So one motivation is that, okay, we want to study the Favard length Kn, so the average length of these orthogonal projections. The observation is that the length of the orthogonal projection Kn is heavily depends on the choice of the direction. So how heavily? So if you look at the projection say psi 0, so this is the projection to the x-axis. Okay. Then when you project here, you have a ton of overlap between these little squares, and the projection in this direction, you actually just get 2 to the power minus, 2 to the power n in these 4 to minus n lines. So actually the length of this thing, this is 2 minus n. This is the smallest possible projection of the set. And so this is kQn. But on the other hand, if you look at the projection direction pi 6, Kn, so which is the which direction is that? This is the special direction. Now let's see if this will work in the picture, where there are basically no overlap whatsoever. There is this special direction, well, I guess it's 2 of them, where these 4 squares, the original construction, they have no overlap. So maybe that's not the end. Okay. So actually you get the full segment here. And then of course, as you iterate, the segments stays the segment. Because each of these segments again gets tiled like this. So here actually, even when you pass the limits, you still see the full segment. So the projection in this direction is the projection of your original square into the segment, and so there is no decay. Okay, so yeah. And then one can ask, okay, so what will be the typical behavior? And this is really what this problem is about.
Is that the fight about 6 or
like
Pascal or 2 or something?
Yeah, which isn't kind of 5 over 6. I'm not sure.
I mean, it's direction in which you have one side twice larger than another, but it's not hypotenuse. So
yeah, okay. Maybe I've tried to make this computation. I thought it was 5 over 6, but maybe I got it wrong. Yeah, my computations are usually wrong. So, but okay. So there is, at least in this picture, it's clear that there is this special line. So, yeah. So then now the problem we're asking for the rate of decay. So we can ask for the lower and upper bounds for this. So let's start with the, let's say, easier question of the lower bounds. So we have the following result of macula in the 90s. Look at the Favard length, and now this will be for an arbitrary compact set E. So this is not just about the four-complex counting. Favard length of E, with lower bound is at a constant by 1 over the 1 Reese energy with a mu for every probability measure E is mu on your set E. And what is the one-dimensional free energy? I1 of mu. This is the double integral, the one-dimensional free kernel integrated twice. So we have such lower bounds.
How do you calculate this?
So tilde means that there is an absolute logarithm constant. Universal constant that does not. I mean, this will be probably 1/6. Okay. Okay, so now maybe we can even sketch this proof because it is really very simple. So let's take as a black box the following identity. So this is classical, let's say, and the proof is also quite easy. The one-dimensional brief energy of the measure mu up to some concept that is the same as taking the integral over all the directions from 0 to pi. And then you take the L2 norms of the projected measures of mu. Okay, so here we look at the push forward of the measure mu under the orthogonal projection. So this is now a measure on the line. And we take the L2 norms of this, if it's fine. Okay, and we're averaging over all the directions. So this is not difficult to prove using Fourier transform. But one-dimensional brief energy is really this quantity up to a constant. Okay. So
in higher dimension, excluding divided in the power.
Yeah, so in higher dimensions, you would put there some power and then you can get the same. I guess that would be co-dimensional.
And then you would constitute capacity, and then you do the slower.
Right. Yeah. Yeah, I think that if you wanted to do something similar in higher dimensions, then you would probably get there the energy of dimension 1 lower. If you're in RD, then d minus 1 energy.
Yes, that's why.
Yeah, so this is basically one dimensional capacity.
Not really.
Well, I mean, you can still look at one-dimensional capacity.
Why not? Anyhow, it's spread uniformly of any.
Yes. So I mean, so because here the measure mu is in the weird plane. This is the plane. So for example, you can take the measure on the Lebesgue measure, the two-dimensional vector. All right. So how do we prove this using this identity? So one thing is, so we're looking at probability measures. So here we put the total measure, total number. We can write this as the integral of this push forward measure, phi theta mu dt. So we're now looking at the total projection power E. This is on the line. And on this orthogonal projection, we're integrating our projected measure. And now, well, we are assuming that everything is absolutely continuous. Okay. So because, I mean, this is trivial if the energy is infinite. So let's assume that the energy is finite. If the energy is finite, then then we get that these L2 norms are finite for all of theta. So we take some theta where this is finite, and now we're right. So we know that pi theta mu, this is absolutely continuous function of the line, and now we can just write it this way. This is somehow by the definition of the push forward dimension. And then we're using pushing forward. Right, that this is the L norm of our measure mu times the length of pi theta of E or 1. That's one pushing forward. And now let's integrate this thing over all the directions from 0 to pi. So on the left hand side, let's say we still have pi. Okay. And now on the right hand side, we have the integral of this thing. Pi theta mu norm times the length of the projection over 1/2. Now let's push it forward again. What else can we do? So then we get the average L norm. Okay. So that's one thing we get, and the other thing we get here, integrate from 0 to pi the length of the projection or 1/2. Right? So that was the second coefficient. And now the thing we got here, this second term, this is exactly Favard length. It's the average length of projection. And this is basically this thing. Okay, so now we have to just rearrange these things. So rearranging with the Favard length, you can square and you rearrange. Your Favard length E bounded from below by pi with squared divided by this integral of the L2 norm. Okay. And now using this formula for the Reese energy, you get that this is comparable 1/1 Reese energy of the.
What do we really assume about the measure mu?
So
Yes, something.
I mean, you assume that it's a probability measure, sure. And now, if the Reese energy is infinite, then this is a trivial inequality. So you assume that the probability measure with finite Reese energy. And that's it. That is okay. Yeah.
So absolute continuity, for example, it doesn't consequence of the fact that you have
absolute continuity with respect to the two-dimensional vector. No. So for example, you could have a measure of dimension 3/2. And then it's one Reese energy will also like that. And you can have a one-dimensional measure, but somehow it's spread it out, but because yeah. Okay, so this was proof. I don't know if I want to have any other proofs in this slide, but but it has the very simple result. It has some it gives some bound for the four-cornered convergence. Or let's try to formula. So the lower bound for the four-cornered convergence. So are there any guesses now what this lower bound might be? If you try to use this result.
So you're asking what I1. What is I1?
Yeah. So let's say that you put the natural probability measure on this nth approximation of the four-cornered convergence. Okay, so let's say that you just take the Lebesgue measure on this little square, but normalize. And yeah, So basically, the way I like to think of the one reach energy is that it's a sum over the scales of the one-dimensional densities, where the one-dimensional density delta mu r, this is the measure of the ball divided by the radius. So now if we have n scales, and the one-dimensional and the four-dimensional canvas is the one outward regular set. So the densities, they're all basically constant at all scales. So if we have n scales, this one-dimensional reach energy is actually roughly n. So what this tells you is that the hard length, the four-dimensional Cantor set, some constant, like one more n, lower bound. And this is maybe, at least when I was first looking at this problem, I was thinking, we have this spectral direction where this behaves geometrically, and I would think that it would be a typical behavior, but it actually is not. So it is also quite exceptional.
So is it, for example, clear that the Lebesgue magnet is, if you're just interested in the reason that it is clear that this magnet optimizes what you can get?
I wouldn't say it's like immediately clear, but I would imagine it can't be much better. Right, okay. So probably up to a constant. Okay, so this is one. And now maybe what is again a little bit surprising is that you can do better. There is a result of Bateman and Holter from 2008. And they get a small improvement over this. They show that the Favard line n is actually longer bounded by log n. And their proof, it does not use any of this energy stuff. It's just like a geometric. Okay. So this is the state of the art. This is the best lower bound we have for fail. And I think that some people believe it to be the opposite.
Was it attempted to somehow estimate numerically?
I don't know, and I would be curious as well. My fear is that this might be difficult to do because the number of these squares increases geometrically. So then but I don't know anything about numerics. But if you know somebody who knows something about numerics and was curious, I would be very curious.
You have a supercomputer on otherwise.
Yeah. Yeah. I mean, I once talking to a guy talking about computation, and he didn't seem to say that this is hopeless. So okay, so these were the lower bounds. And now let's get to the meat of the business, which are the upper bounds, where much more has been done, and where things are much bit more difficult. I don't know if it's fair to say that things are much more difficult. I mean, the proofs that are in the upper bounds are much harder, but then maybe this is not optimal. Maybe it can be improved, and then maybe it's just even harder. I have no idea. But okay, let's get upper bounds. So this is what Peres and Solomyak originally did. So their paper in 2002, where they started the whole business, they proved the first quantitative decay ions. They were extremely slow. they prove that at most the exponential function minus constant time log star n. For now, what is log star? So it's something has some power in the name. I don't remember exactly, but log star of n is the minimum integer k. But that if you iterate the logarithms k times and you apply it to n, this goes below 1. That's an extremely slow growing function. And they prove this kind of upper bound. So, and I mean, they have the lower bound 1 over n, and they prove this upper bound that's nowhere near that. Okay, so then a couple years later, another Peres and Solomyak proved a much better bound. That's from 2010. They proved that the Favard length n is at most constant divided by n to power 1 over 6 minus epsilon. So now the constant depends on the epsilon. So they got this kind of polynomial decay, arbitrarily close to power 1 over 6. And this is the state of the art again. Like nothing better has been shown since then. So one comment about Peres and Solomyak result I forgot is that this is not just for the four-cornered Cantor set. They proved it for pretty arbitrary self-similar sets with strong separation conditions. Whereas here, this is really for the four-cornered Cantor sets. All right, so now we basically hit the wall with the four-cornered Cantor set, but people still want to do something. So now maybe we can prove something else for some other kinds of sets. So what is known more generally? More for other kinds of sets. So of course, you can ask the same question for all sorts of self-similar sets. More generally, we have the bound bar length, now let's call it En, or En is now some kind of self-similar set, and we're looking at the n approximation of it. With some bound of the polynomial type, so 1 over n some power c, okay, for the following sets. So we have that for the principal graph. This was done by Buffon and Favard. Then for the self-similar set with 4 similarity, and this was done by Buffon, Favard.
This is without any separation.
No, this is also with some good separation with which now I don't remember exactly what they assumed, but you could probably think always that maybe you have a square and then you want to put 4 squares of side like 1 over 4, okay, which are disjoint, okay, and then you iterate that. Okay, so it's really quite simple. Yeah, in terms of like some more complicated separations, then I'm not sure if Peres and Solomyak is mean, I will say about this in a second because I get confused about different separation conditions. Maybe you can tell me. Okay, but just here to finish the list of sets for which there is polynomial decay. There are some, but not all, rational product sets. This is one of them. A rational product, it means that eventually you divide your set in kind of grid. Okay, but then you just say that certain digits are allowed and certain are not allowed in such a way that you get something of dimension 1. And then for some sets of this type, they get also this geometric decay. Okay, but now for general self-similar sets, but now with some good separation, what it means, so I think they literally in the paper they write you have a circle or you have a disk, and then you choose L disks of side length or diameter 1/L, and you place them in your original disk so that they are disjoint, and then you iterate this. So does this cover all, I don't know, strong separation conditions of similar set or not?
Well, maybe
I'm not
in the homogeneous space because you
right.
want the same.
So yes, so they are homogeneous. I think here Peres and Solomyak actually also allow different subtraction. As long as we get something of dimensional.
Okay.
So here they have, or not homogeneous, here they have always the same subtraction. Anyway, so for such inside generality, they don't get this polynomial decay, they get Favard n, but most the exponential minus constant and then square root of the log. So instead of the square root, there was no square root, then that would be the full one. How far they are. And this is due to bonds and volts. And now all of these upper bounds, except for the Peres and Solomyak is fairly geometric, and I think it's more of a dynamical systems kind of proof. But now all of these other proofs, they rely on some machinery that I honestly don't understand. So they do some hard things involving trigonometric polynomials. Then they're interested in the zeros of these trigonometric polynomials, and then depending on the structure of these, for example, the structure of how you choose this digit sets here, either they get something or they don't get something, and then they do some algebraic stuff, and they do some number theory, and that's how they can squeeze out some cake. But I tried to understand it at some point, and I was wrong. But that's how they did it, and this is.
But I didn't get it because I didn't really get how you define the set. What is the direction? First, you think I'm going to use these polynomials, and then I will cook up a set that fits them, or is the other way?
It's the other way. So they have some machinery so that to certain set. Well, even here they do this. So given some nice enough self-similar set, so they get some separation, they can associate it with certain trigonometric polynomials. And then they want to get some lower bounds on some integrals for these polynomials. Also, not over the whole line, because then it's integrated to 0, I guess, but only over some range, over some domain of integration. And then for certain trigonometric polynomials, they can get these bounds, and for others, they cannot. And then if they can get these bounds, then they get decay. If they cannot get these bounds, then not. And also depending on how good their bounds are, they either get a weaker decay or better decay.
But these polynomials, they're one-dimensional, on the circle or on the torus?
They are one-dimensional. I think they're one-dimensional. And then, so for example, I think Wabash was very interested in also in this, because then this was tying it to this number theory thing, which, yeah, depending on the zeros of this. I don't know. I like this was really always went over my head. But there is a nice survey to this. There is a survey due to Waba from I think either 2012 or 2015, something like that. And it's still something like recent progress on the Favard length problem. Something like that. And there she tried to describe it a little bit more in a more accessible way. So whatever I understood from that survey. Okay, so this is this hard stuff for the deterministic sets. And now I will move on to the random sample sets where actually things are much easier and we can get much better bound. But before that, the motivation, which was asked at the beginning. So the reason why I am interested in this, and the reason at least that was mentioned in some of these papers in their introduction, I guess they at least had it in the back of their heads. When working on this, the following. So there is a lecture to be complete. Pretty old, so it goes back to 1967, and it predicts that the Favard length of the set E after bounded up to a constant by something called the analytic capacity of the system. Maybe now I won't define what analytic capacity is, but it is something related to bounded analytic functions. It's something coming from complex analysis and the study of provability. So now the thing is that for nice enough self-similar sets, okay, we can actually compute quite explicitly this analytic capacity. So for such set, we know that the analytic capacity, this end approximation of the set, this is comparable to 1 over n power 1 per. Okay. So now, if the Dimitrov conjecture is true, this implies that for all such similar sets, for which now the best bound is this, we predict that the Favard length of the set is at most the constant 1 over n. And in fact, it should be true for arbitrary sets without any dynamical systems structure, right? So the fact that having all this structure, the best we can get is something like this, and in that using some number theory algebra magic. Whereas here, it's predicting that we have a much stronger bound without having access to all these tools. This is perplexing. So my strong belief for quite some time was that this conjecture is true, and that these complicated tools they are using, they're just not fit for the job, and that some new technology should be invented. But now I've gotten very frustrated with this, so now I'm maybe getting to the point where I'm thinking that the conjecture is false, and that, you know, maybe now I'm more interested in getting the lower bounds. We're not so much looking that. Maybe trying to show, for example, that this is not very far from being sharp. Maybe inventing some kind of self-similar sets for which you can get the lower bound violated in this thing. If you can violate this, then well, this is a quantitative version of this conjecture, but actually this would has some also qualitative implications, and it can be very, very long.
So is the conjecture known in any reasonable generality for any class of sets?
So, okay, so the original conjecture was not like this. The original conjecture said that a Favard length that E is equal to 0, you can only get the non-capacity of E. Okay, so it's a qualitative conjecture originally, but now, and this is true for certain finite length. But one of the implications is false for set of infinite length, but the other implication is not null. So now the thing is that the annual implication, so when it's open is whether having some E positive, you would apply the term that this implies that some E is positive. Okay. For general sets, so you would like to show this for general sets, and can be shown that this is equivalent to this. If you want to have this for general for arbitrary. If you have a set which violates this, if you have a set which violates this inequality, then I can hook up. Okay, so that was a bit of motivation for why I am interested in this and why I think some of these questions were asked in the first place. So now moving on to the random counter sets, or a little more known. So things are very difficult for deterministic sets, but as soon as you add some randomness to the picture, turns out that you can get pretty sharp bounds with not so much effort, or at least not so much compared to the deterministic case. So the first kind of random counter set for which people started studying the Favard length was again in this original paper of Peres and Solomyak. And the random model they studied, so maybe first I will write the proof. So for some kind of random counter set, they proved that the expectation Favard length is n. This is actually comparable to 1 for n. Where the lower bound is this easy bound you get using the energy methods. So then all they had to do was prove this upper bound. And it turns out that it matches the easy lower bound. So what is the set En? What is the random model for which they prove this? So they consider sets that look like this, have a unit square. Then you divide it into the 4 subsquares. Each of these subsquares you again divide into 4. And inside each of these subsquares, we choose one randomly. With an equal probability for each of the 4, and so that we do this in an independent way. And so this is how you get, let's say, E1. And then to get E2, you repeat it within each of the squares that were chosen. Again, everything is independent and with equal probability. So for such sets, they prove that the Favard length actually behaves in the way that it should.
Can you repeat how you choose squares for E1?
Yes. So first you divide your original unit square into 4 equal subsquares. And each of these 4 subsquares, so let's mark them like this. And then each of the 4 subsquares, you again divide into 4 subsquares. And from each of these 4, you always choose one randomly. So that after one step, you get 4 subsquares of psi 1/4. So then as you iterate, you do get something with positive exponent length.
But when you say it behaves as you expect, you mean in the sense of average, not almost sure or not.
Yes, yes, so that's true. But now, and this is very, very neat, there is the very recent result of Chang, and Solomyak. Last year, where they consider, maybe I don't want to state exactly what they do, but there's a more general random grids. So this is in particular covered by their more general result. Okay. And then they prove, so for one thing they prove that the Favard length En, this is on average. Now there's a funny dichotomy. So if you make a certain assumption about your random model, then you get 1/n. And then if you don't make this assumption, or rather if you assume that this extra condition does not hold, then you get log n over. So there is some dichotomy, okay? But either you behave more like log n over n, and this is kind of similar to the 4 corners Cantor set situation, or you have 1/n. And they also prove, and also they prove something like the path En multiplied, let's say you're in this situation, and multiplied by n, then it proved that this converges to some constant volume. And they even compute this constant, and then it depends on something. Like they will do something really neat. Okay, so this is something very recent.
Yeah. But these are technically not so similar sets in very often, right? Because we use different.
Yeah. Okay, so this is all I know about random grids. And then there's
the method scheme is so again related to energy or
no. So this is and I don't know these very well, but I think there's something like you pick a line, and then you're asking, does this line intersect my set? Okay, and then you know maybe that your line intersects your set at a certain generation, and you're asking, as I'm passing to the next generation, does it still intersect my set? So there's something like extinction something something. And they use these estimates. I think especially here they do some significantly more sophisticated estimates to get whether as you to get estimates of the probability that after a certain number of steps your line still intersects your grid or not. So I guess these are more probabilistic, right? Okay, and now, so these are the 2 results that are about random grids, and then there were 2 other kinds of random sets that were considered, which were related to disks. And so, how does this look? As it's stated, the theorem, one is due to Chang in 2018, and the other one is due to Favard and Dąbrowski. This is from 2024. They proved there that again, the expected expectation of the Favard length expectation of the Favard length of and that some iteration is comparable to 1/10. And then for again it is followed. So the construction there is like you start with a unit disk. And now you would like to put there 4 disks of side length diameter 1/4. Okay. But now the thing that you always want to put them this way, so that they are touching the circle and that they are say rotated by I/2 each of each other. Okay, so you basically you have this 1, 2, 3, 4, and then you want to rotate. So what you do is you have a sequence of rotations, so the omega 1, 0, omega 1, 1, which are IID uniform on the 0 to pi. And then after each step, you just say, okay, I want to place my 4 disks in this configuration, but just maybe rotate it in some way.
But inside each disk, you rotate in the same way.
Okay, so now here's the thing. So I wrote here 2 different papers. So the first paper is that inside you have, let's say, omega 0, omega 1, yada yada, where omega k tells you how you rotate at the k step, but then in each disk is the same. Whereas here they say, okay, let's rotate independently inside each disk. So then here you may rotate in a different way, here in a different way.
So what happens to this construction if you make it non-random? Does it behave the same as the Cantor set? So you just don't rotate.
If you don't rotate, you get exactly the coordinates. Okay. So this is what they work with. And now the
one where you the more recent paper is the one where you rotate everything
independently, yes. Inside you have more randomness. You have more
randomness.
independent.
And it becomes more difficult when you have more randomness. Because usually somehow more randomness makes things easier.
I would say it's very similar. Okay. I would say it's very similar. So in this paper with Chang and Giacomo, which we're finishing up at the moment, we do is we prove the following. So maybe before I write what we get, I will look at the model. So we started the same way as in this random disk from before. We have a unit disk. Now we want to place 4 disks way. But the difference is that now we introduce some parameters that tell you how big are these 4 disks. Okay, so this is maybe radius R1. Okay, and now inside each of these, we again want to. Now these will have radius R2. And so on and so on. I mean, at each generation is a fixed radius, so they don't change between these 4. But they can change from scale to scale. So whereas in this original papers, on the at k generation, you had disks of diameter 4 to the power minus k, whereas here this can change from generation to generation.
And we still have rotations. We
still have the rotations. Okay, and we can actually work either with one model of rotation or the other, with just a teeny tiny, like it's literally one line changing to make it work for us. So the only relation to these sequence of radii needs to satisfy is that, let's say, k plus 1 generation comparing it to the previous one, this has to be smaller than 1.1 divided by 1.5, maybe not the optimal, but the thing is that we don't want these radii to start intersecting. So basically, if we had no restriction like this, then maybe you would be able to put 4 disks that are very big, and then everything would get ruled. This 1.5.4 tells you that it's going to happen.
But then you can end up with a set of dimensions smaller than
It may have dimensions smaller than 1, it may have dimensions bigger than 1 as well.
Right.
So for example, if it is always 1.5.4, you will get a self-similar, well, not self-similar because it's randomness.
random sets.
Yeah, random self-similar set from dimensions typically greater than 1. And this and it's over. Okay. But now what do we prove for this? So these are the sets we work with. What we prove is at least an expectation, and maybe we will get also, since we have Alan Chang on the team, then maybe we will also get the almost sure thing. We prove that this is comparable to 1 over energy. Where now mu n is this natural probability measure on the nth step of this construction. So we again get that this lower bound is sharp for this kind of set. Where now this, if you choose these radii so that, for example, we get something lower dimensional than 1, okay, then this energy will blow up. No, sorry, yes, it will blow up faster. So then this
convergence have to how fast, right?
Yeah, exactly. So this is this is really telling you exactly how fast it is depending on how you choose this radii. And for the last minutes, I can say a little bit about the proof.
Instead, you change the distribution.
So we can do either one or the other. So yeah, you could say that you either choose one random model or it's the other random model. In both cases, this is the kind of power length estimate you get. Okay, so proof idea. Maybe I don't want to torture you for too long, so I will not say everything I have prepared, but just 5 lines. So let's say that we're looking at this. So let's say for sure what happens in this random model where you have fixed radii, in the sense that we're looking at the result of Chang. So there we always have 4 disks of radius 1 over 4, or 4 times smaller than the previous one. Okay, fixed geometric sequence. So in Chang, so let's define AK be the expected value of the length, the orthogonal projection of the set EK. Okay. So we took k generations, k steps of the construction. So now we have 4 to the power k disks, yada yada. And now I'm asking, what is the expectation of the length of the orthogonal projection? But now well, okay, but here we have theta, and on the left-hand side we don't have theta. Ah, but this is all rotation independent. So while for the four corners Cantor set, there was this heavy dependence on the length of projection depending on the direction. Here, at least taking expectation, it really doesn't matter. It really doesn't matter because whichever projection you look at, since you're taking expectation over these rotations, so we can define such a sequence which does not depend now on theta. And without a lot of generality, we can maybe look at the projection on the x-axis. And now what we would like to do, sorry, and since this does not depend now on the projection, this absolute constant, this is the same as the expectation, the bar length of p. So now, our goal would be to show that, say, AK it decays like a C over K. That's what the result of Chang proposes. So now most of the paper is used to prove the following lemma. We actually have this recurrent inequality that if you look at AK plus 1, this is bounded from below by AK minus some absolute constant times AK squared. Or in other words, when you look at the expected length of projection on the K plus 1 step, you can bound it by the length of projection of the K step minus some gain. Right? So this is what the lemma says. And now, now how can we use this kind of recurrence inequality to get this? And now I think I lost the part where I wrote this down, so let's hope I can actually write it down. So you do this by induction. So how do we use this to get the decay of C over K? So assume that you already know that AK is more equal than C divided by K. And now we want to prove the same for AK plus. So then AK plus 1. Well, we have this. We write that this is bounded from above by AK minus constant with little c times AK squared. And now this is bounded from above by when we plug this in here. This is big C divided by K minus little c times big C squared over K squared. Now, why can we do this? So the reason is that this function t minus ct squared is monotone increasing on some little interval around 0. So since this is monotone increasing, then we can now plug in this bigger value here and get it before. Right. So this is completely elementary. And now we can write this. So what is this? This is like t times k minus little c times big C squared k squared divided by k squared. So now, sorry, there is ck minus c squared. This right. Yes, this is right. And now here we have some capital C, which I haven't said what it is. So we choose capital C to be the inverse of the little c. So we take b1 over the little c. And then this means that this speed is enough with one of this speed. This is what we get. We get capital C times k minus 1 over squared. Then it so happens to be left or equal to C minus 1 over k. Okay, so this is fairly okay. And now I had prepared how do you prove this, but maybe I will skip this because we've been here for a while already. And instead I will just say what's different now in this model where we allow the radiated change between this generation. The right one. So there's some geometric argument for how you get this lemma. And we do essentially the same, we follow essentially the same geometric argument. Maybe it gets a little bit complicated at some part, but not that much more. And we also arrive at some inequality. So in this paper, CDEL, we get that the expectation, the length of projection of the k plus 1 step is the smallest, and now it's kind of a drag, right? 4 times rk plus 1 divided by rk times k minus 3 times 4 times rk plus 1 divided by rk times ak squared. Okay, so we arrive at this kind of inequality, still at recurrence, but it's kind of painful because here we have a bunch of parameters. But it turns out that it still can be solved, just not as easily as this one. And can be solved, prove that AK bounded from above, some constant times 1 over sum from J 0 up to K. And here 1 over 4 power J RJ, which looks kind of horrible, but this is really the same 1 over 1. This is roughly J. And yeah, I'll finish here. Thank you very much.
So the question is there a chance to use this result about the random context set to construct a two conjecture, for example? I mean, by estimating gamma.
No, we are hoping. I mean, so the thing is that we are sort of hoping for something like this, but analytic capacity it also satisfies this estimate. So you can't focus.
Analytic capacity is logarithmic capacity.
No, so analytic capacity. So analytic capacity is defined in terms of bounded analytic function. And I always forget the actual definition because I only use some characterization of it. The thing is something like the analytic capacity is that E is either supreme or infimum of the F prime infinity, whatever that is. And then you're looking only at constants F, which are defined on C minus E, and which are holomorphic. Sorry? yeah, either soup or ink. I should know it, but I didn't.
So these, in general, questions about Favard, do I have not for high dimensional counterparts? Or is it
Yeah. I mean, you can ask. You can look at this thing they're called integral geometric measures. So you can look at the length of projections of the right dimension. You can average over this thing.
when you look at this in the Grassmannian approach, which you also related?
Yes. So then there's I think I'm only aware of one result in this direction that's very recent. So I think Caleb Markle. He was a student of Peter Melalava. Recently he proved that let's say it's the higher dimensional path. So I guess he works with d-1 dimensional sets in R3. I don't remember it, but that works with some sets in higher dimensions. So and to get there again, kind of polynomial decay. And it's all both for some higher dimensional counterpart of the orthogonal transfer set, but also for some more general product set. It's possible that maybe he only looks at one-dimensional sets in high dimension. But yeah, it could be done. Yeah, it would be natural. I don't think it's invalid.
So the methods in the proof of this lemma, is it just some geometric considerations or?
Pretty much. So there's like one line I could write about this. Yes, maybe I can write one line. The one line would be that say that you have this one disk, and here you have a smaller disk. Okay, and now you want to compute the AK plus 1, let's say. So then so you're interested in the length of the projection of the set E K plus 1. And now this is associated with some sequence of rotations, so omega 0 up to omega k. And now the trick is that you decompose it into the projections of these four disks separately. So you write that this is equal to the length of the I0. Now let's call it U1, U2, U3, U4. J. Okay. So the J from 1 to 4. And then you have to subtract the overlaps between the two. So J different than K. Phi 0 UJ intersecting with phi 0 of UK. And now these things, I mean, they are scaled by 1/4. So this basically, well, after you take some, after you take the expectations and so on, this will correspond to AK1. This will correspond to AK. And these things will correspond to the small constant times AK squared.
You use independence and also
Yes. Here you use independence, and also, I mean, another thing that you use is that So here I wrote that the measure of this set, this is the sum of these subsets minus the intersections. And then I guess wasn't that important? Yeah, no, sorry, never mind. So yeah, this is the gist of it.
And I guess that it's quite important that you assume that those circles, they are evenly, they are, in the same distance from one another.
So you're asking if you can do something like, instead of having them like this, maybe have them like that?
For instance.
Yeah, as soon as you start breaking some symmetries, I'm not quite sure. Yeah, I mean,
But when you average over rotation, you can see.
that's the thing. When you average over rotation, maybe it still go through, as long as they are just joined, maybe at some fixed distance. Yeah. Maybe it would still go through.
And another question, is anything known about the overlapping phase? I guess that the upper bounds, we should get the same upper bound, but the lower bounds should be more different. But maybe that's wrong.
So when by overlapping case, you mean that you start, let's say, with 4 disks, but they are allowed to overlap?
For instance, yes. So basically any either random or non-random, EFS type construction with overlaps. Is there like anything known about the?
So if you have overlaps, can you still have positive length and so on? I mean, you could still ask about even if length is 0, you could still ask about how fast it decays. And so on. I don't think anything is.
Yeah,
I remember that one of these conditions is equivalent
to having positive Hausdorff measure in the dimension.
Yes. Either the opposite condition or one of these, but then yeah.
Well, yeah. If Mercury is already on the business, then okay, any more questions?
And you show that two extreme right? That can be physicality there. Now I'm thinking about theta as my
Yeah, so there is in the paper of of Damian Dąbrowski, that was the paper where they proved that the Favard length Kn lower bounded by log n over n. They proved another thing with lower bound on the median code. So they proved that for at least half, so they also showed for at least theta, you have the length of the Kn. This is at least 1 over n. I think they showed something like that. And I don't remember exactly the proof, but I remember it was fairly short and not that complicated actually. So if there is something, if the Favard length is to be really large, if for example this is very long sharp, and there has to be a fairly small amount of directions that are responsible. I hope that I get somebody here interested in this business, because I would like more people to be working with these things, because I am very much frustrated by maybe the lack of progress in the recent years. At least on the fourth one, it's the case, the one where it will start.
Okay, any more questions? No, so let's make them again. You are invited to folklore and group campaign with Madure.
For the day.